Hello everyone, I'm Hemanth Chowdary, a cybersecurity intern working for CyberSapiens. Today I'm going to give a presentation on cross-site scripting vulnerability on how it works, different types, and the preventative measures. Let's get started with the basics then. What is cross-site scripting vulnerability? It is an injection attack that involves injecting malicious script into trusted websites. These aren't the scripts that website owners intended to be there. These malicious scripts are executed in the victim's browser, so it's not the website server that is directly harmed in this stage, but the user visiting the compromised page. This works because the victim's browser trusts a website origin. If a malicious script appears to be coming from a legitimate source, the browser will happily run it. Now let's see how the XSS works. The XSS attack lifecycle. It all starts with the attacker identifying a vulnerability. This usually involves finding the input field on a website that doesn't properly validate or encode the data that you enter. Think of search bars, comment sections, or any place where the user input is displayed back to them or other users. Once a vulnerability is found, the attacker crafts a malicious script. This is very often done in JavaScript because of its tight integration with the web process, but it could also be other client side scripting languages as well. The attackers then inject this script through the identified vulnerability. This could be through a URL parameter, a form submission, or any other way the website accepts user input. The next step is when the victim visits the compromised page. This could be because they clicked a specifically crafted link sent by the attacker, or simply because they navigated to a page where the malicious script has been stored. Finally, the victim's browser receives the web page, including the injected malicious script. Because the browser trusts the origin of the website, it executes this script without question. For the simplified understanding, just check out the diagram. Here, first, the perpetrator discovers a website having a vulnerability that enables the script injection. At the second stage, perpetrator injects the website with the malicious script that steals each visitor's session cookies. At the third stage, for each visit to the website, the malicious script is activated. Once it is activated, at the fourth stage, visitor's session cookies is sent to the perpetrator. So that's how this attack cycle works. Types of cross-site scripting vulnerabilities. There are three major types of cross-site scripting vulnerabilities. First, reflected cross-site scripting vulnerability attack. Second one is stored, and the third one is DOM-based cross-site scripting attack. Now, let's learn more about these vulnerabilities in details in the upcoming slides. Let's start with Reflected XSS, also known as non-persistent XSS. In a Reflected XSS attack, the malicious script is part of the current HTTP request. Think of it as a temporary injection that doesn't stick around. The script is then reflected back to the user's browser in the server's response. The server isn't permanently storing the malicious code, it's just echoing back as part of the page. Because the script isn't permanently stored on the server, this type of attack often requires social engineering. The attackers needs to trick the users into clicking the specially crafted link that contains the malicious script. This crafted link, when clicked, sends the malicious script as a parameter in the URL, and the vulnerable website then reflects the script back to the user, causing their browser to execute it. Now let's look at the diagram to get the better understanding of the reflected XSS attack. First, the attacker sends the malicious email containing the malicious link to the victim. In this example, http:/bang.com/ whatever the script that is injected into the URL. Now, the victim clicks on the link, sends the request to the vulnerable bank.com website. At the third stage, the vulnerable bank website takes the data from the request and includes in the valid web page. The fourth stage, victim's browser now trusts the attacker script is from bank.com. And after this is all done, at the fifth stage, attacker has full access to the victim's account. This is how the attacker takes over the account of the victim. Alright, now that we completed the theory part of the reflected XSS, let's see how it works in the simple lab on Portisco website. Well, there are a lot of these kinds of labs that are available on Portsfigure if you guys are curious as to how the different kinds of vulnerabilities work. So if you guys have some free time, check out the website and check out these labs. Now, regarding reflected access. In this attack, we know that the website is vulnerable. If the website is vulnerable, the script is injected through the HTTP request, i.e., in this example, we can inject the malicious script using the search bar. Now, let's use this basic script in the search bar, and if it works, the number one should be reflected on the website. So, yeah, let's try this. Now, let me just copy this and paste it here and click search. And yeah, look at this. The script worked, and now the number one is reflected on the website. And see, this is how reflected XSS looks like, and this is how it works. Next up, we have stored XSS, also known as persistent XSS. This is generally considered to be more dangerous than the reflected XSS. The key difference here when compared to reflected cross-site scripting is that the malicious script is permanently stored on the server. This storage can happen in various places, such as databases, forum posts, comment sections on blogs, or even in user profile information. The attacker would inject the script directly into the server through them. The script is then executed whenever user accesses the affected page, so it's not reliant on specific malicious link being clicked each time. This makes stored access more dangerous because it doesn't require that initial trickery of getting someone to click a link. The attack happens automatically for anyone who view the compromised content. Now let's get the better understanding of the stored accesses using this diagram. First, the attacker gets the malicious data into the database. We don't require social engineering for that. Second, the entirely innocent request was sent by the victim to the server. And at the third stage, the bad app retrieves the malicious data that was sent by the attacker and uses it verbatim. And because since it uses it verbatim, now it runs the malicious code and retrieves the data accordingly. At the fourth stage, the response includes malicious data as active content. And when the attacker gets the hold of the information that he requires, bam, that's how the attack happens, or the account is being taken over, or they get access to sensitive information. Now let's see how stored XSS works in a lab setting. As we know, in this attack, the malicious code is stored in the server side permanently. Now in this lab, we're going to use the comment section to store the malicious code. And let's go into the comment section. Let's go into this post now for now. Scroll down, and as we can see here, this section to leave the comment. And in this place, we're going to use the script that we have used in the previous lab, and that is script alert1 script. And here let us use a name. Come on the website. Then when we go back to this same blog, the number one should be reflected on the blog itself. So let's see if the script worked. Let's post this comment. And thank you for submitting the comment. And let's go back to the same blog again. And as you can see here, number one has been reflected on the website. That means the script worked. And this is how stored XSS looks like. The third major type of XSS we'll discuss is DOM-based XSS. This one is a bit different as the vulnerability lies in the client-side JavaScript code itself, rather than the server-side code directly. In DOM-based XSS, the malicious script is executed due to the unsafe handling of the data within the document object model, or DOM. The DOM is essentially the structure of the HTML page that JavaScript can interact with. What's interesting about DOM-based XSS is that the HTTP response from the server might not actually contain the malicious payload. The vulnerability exists purely in how the client-side JavaScript processes the data. This often involves manipulating the URL, such as through query parameters, the part after the question mark in the URL, or the fragment identifier. the part after the hash symbol. JavaScript on the page then reads this data and uses it in unsafe way, leading to the execution of attacker's script. Now let's look at the diagram of the DOM-based XSS. First, the attacker grabs the URL containing the malicious string and sends it to the victim. Then, the user is tricked into opening the link and requesting the malicious URL to the website. The website receives the request but does not include the malicious string in the response. And then, the user browser executes the legitimate script inside the response, causing the malicious script to be inserted into the page. And this is how the malicious link gets stored in the server side. After that, the user browser executes the malicious script inserted into the page by the client-side code. And at the last stage, the user-sensitive information is sent to the attacker's server. And that's how the DOM-based XSS is done. Now let's work on the DOM-based XSS lab. This is the lab that we are using for this vulnerability. This lab contains DOM-based cross-site scripting vulnerability in the search query tracking functionality. It uses the JavaScript document write function which writes data out of the page. So this is the vulnerability that exists in this lab. To solve the lab, we have to perform the cross-site scripting attack that calls the alert function. So in the end, we have to get the same result. Like once we perform the attack, the number one should be reflected on the website itself. So that's how it's gonna work. Let's get on to it. Now let's input an alphanumerical string into the search bar. I think yeah, I already typed it here. ABCD1234. Let's type this and search. And now this has been inputted into the website. Once it's done, let's go and inspect the HTML page. And in here, let's search for the numerical string that we have inputted. ABCD1234. As we can see here, the alphanumerical string that we have used in the search bar is being inputted into image src. That means the string is being inputted into the HTML code itself. So, in theory, if we put a script here, it should be reflected on the website. So that's the DOM-based vulnerability that this website have. Let's test that theory. Let's input a script in here and see if it works or not. And in order to test this, let's get out of the inspect element tools. And now let's input this basic command into the search function itself. svg onload alert 1. Should we? And if this works, then the number one should be reflected on the website. That means this website has DOM-based XSS vulnerability. And this is how XSS DOM-based vulnerability looks like. Alright, now that we understand the threat, let's talk about how to prevent XSS attacks. One of the key strategies is input sanitization. It involves carefully examining and cleaning any data that is supplied by the user before it's processed or stored. This often means removing or escaping potentially harmful characters that could be part of the malicious script. The goal of the input sanitization is to ensure that the user's applied data is treated as plain data, not as executable code. Another critical prevention technique is output encoding, also often referred as escaping. Output encoding focuses on treating user supplied data as plain text and when it's displayed back to the user. This involves converting special characters that have meaning in HTML, JavaScript, CSS, or URLs into their safe HTML entities. For example, the less than equal to character is converted into and lt semicolon and the greater than equal to is converted into and gt semicolon. Unlike input sanitization, which happens early, output encoding should be applied as late as possible, just before the data is rendered in the user browser. It's also crucial to use correct encoding methods for the specific context where the data is being displayed. For example, encoding for HTML is different from encoding for JavaScript or an URL. Our final defense mechanism that we'll discuss here is Content Security Policy or CSP. CSP is a browser security mechanism that allows you to control the resources that the browser is allowed to load for your website. You implement CSP by setting the content security policy HTTP header in your server response. This header allows you to restrict the origins from which the browser can load various resources, such as scripts, style sheets, images, and more. One of the key benefits of CSP is preventing XSS, is that it allows you to prevent the execution of inline JavaScripts, scripts that are directly within HTML tags, and also disable dangerous functions like eval brackets, which execute strings based upon JavaScript code. And by applying all these security policies, CSP adds layers of security and fulfill the defense in-depth strategy. Well, now that we have gone through the whole presentation, these are some of the key takeaways. We learned about XSS, how it works, and we also learned that XSS is a persistent web security vulnerability. We also learned the different types of XSS like reflected, stored, and DOM-based. We learned about the prevention methods such as input sanitization, output encoding, and CSP. We have to emphasize on safe security coding practices and regular security audits so that we could find these vulnerabilities as quickly as possible and we can rectify so that they won't be exploited. These are the sources and labs that I used to make this presentation. Labs from Ports Figure and sources from various websites that I found online. Thank you for listening to my presentation and remember, stay secure.